All right, so we are still working in the waves unit,
Yeah.
but looks like with this assignment, we're going to dive into a different kind of wave known as standing wave.
Actually got a chance to look into the lesson.
Okay, good, good. So are there any things that stuck out to you that were things that you wanted to ask about from your reading?
Back my notes real quick.
Sure.
Not really.
Okay.
But I looked into like how they describe the fact of how they when you look at the wave, it's more of a loop instead of like a swirly line.
Right,
and
right.
One loop is equal to half a wavelength.
Yeah.
I also brought in the nodes and anti-nodes.
Right.
Both on a wavelength.
Yeah, and did you read about a word called harmonics?
Yes, yes, it is.
And so there's like a whole series of harmonics, first harmonic, second harmonic, so forth. Didn't you say actually you play the guitar?
Mm-hmm.
So
yeah, they referenced it like strings on the violin or guitar.
Okay. Have you ever actually played a true harmonic on a guitar before?
Yeah.
So there's that special spot that you can place your finger, and you don't press.
And then like all the strings just like harmonize.
So actually, it's just like one string at a time. There's a specific. So let me try to draw a picture here. So let's say this is your neck, and then you got your frets, and then let's say your guitar is over here like this, and then here's your this, and so obviously up here, and then so when you actually here's the bridge back here, and then when you have a string that goes, and the length of that string is just the length from here to where it's tied on here, right?
Yeah.
However, when you press your finger down, let's say you press your finger here, this is now your finger placement here, what happens to the effective length of the string? Shortens, exactly. The length of the string is clearly still the same, but when you're trying to make a string make a sound, the length of the string you're referring to is how long is the string portion that's actually vibrating.
Yeah.
And so when you exactly, so when you put your finger there, you now have a new length that goes from here to here, right? And that's shorter. This portion right here is still there, but when you pluck the string, is this portion right here going to be vibrating?
Where?
The portion that's up on the yeah, this portion right here, when your finger is in this position, and then you pluck, anywhere in between here and here, this is the portion in here, in between here and all the way down here. This is the portion that vibrates, right?
Yeah.
And so there ends up being a very special spot on a string that you place your finger on the fret, and you actually don't press it in fully. You actually have to do it quite lightly. And then when you gently pluck the string, you'll get this beautiful, almost sounds like a, have you heard a harpsichord before? I don't know if I'm saying that right. Harp, or like a harp. You know the sound of a harp?
Yeah.
So have you ever gotten that sound out of a guitar before?
Yes.
Okay, because if you've done that, that means you are actually playing the harmonic, and it's a pure harmonic of that particular string, and it gives that very pure, beautiful, like kind of like that sound.
Yeah.
That's and you notice right away that it's a very different sound than you'd expect to come out of that string. Nonetheless, there's all these different kinds of wavelengths that you can potentially get when you pluck a string, and each of those that you referred to, like the loops when you refer to loops. So like in a picture, if you had just a string that goes from here to here, and then you pluck it, the simplest vibration pattern that you can get from this string would cause the string to, let's say, or I don't know, let's say with your finger you pull it down like this. So you're pulling it down and then you release it. That string will of course go back up and it will come up to here, and then it will just repeat and come back down. It'll go back and forth like that. That's the simplest possible vibrational pattern on the string. It's called the first harmonic, and that provides a very low bass sound. And that, as you had said, has how many loops? One, exactly. But on the other hand, if I extended this and I didn't prepare my drawing well enough, you can imagine this goes over to another side, right?
Yeah.
If this was now the full length of the string from here all the way down to this other point that's over here, then when you pluck it, you can still get this loop here going up and down, but you'll see another secondary loop going up and down as well. And that ends up being called the second harmonic, and it has two loops. So the point being, I'm just trying to illustrate this idea that there's different patterns that you can create on a string, and each of them provide different pitches or frequencies. So when you as a guitar player, when you're playing a high pitched sound, that's like considered a high frequency. And that means that when you are playing that, the actual string, if I can relocate where I always lose where the pen is. Hold on a second. There it is. So like your string might be going up and down many, many times. And these are actually, it's almost impossible for me to draw on here. But something like this, the string itself is now vibrating. You probably saw this in your textbook like this, right?
Yes.
So when you have tons of loops in there and the full length of the string goes from here to here, that would be the slow motion vision of a high pitched string that's vibrating. Bing! And that means it's a very high frequency. It means that it's going back and forth many, many times per second. Where if you plucked a different string and it only produced, let's say, 3 loops like this, that's a lower frequency. And when you pluck it and see that pattern, you'd hear like a burr, lower pitch, means lower frequency. And that means that string is not vibrating back and forth as many times per second. Because you remember that frequency as a word refers to how many times per second something is happening. So when you're dealing with waves and waves on a string, known as standing waves, frequency is related to how many times the wave vibrates. So let's come back to this picture on top. It's referring to how many times it vibrates per second. So if you looked, at this point right here, if this point on this string went all the way down to here and then all the way back up to here, and it took exactly 1 second for it to do that, guess what the frequency of that wave would be? One. Yeah. What would the unit be for frequency? Hertz. Exactly. Yep. 1 hertz. And that would be really low. That would be an extremely low sound. You actually wouldn't even hear it. The minimum frequency you can hear in your human ear is 20 hertz. So literally like the lowest sound imaginable that you can imagine, which might be like a thunder, lightning strike, or elephants also make these extremely low rumbling sounds. Those will be somewhere around 10 or 20 hertz. And your human ear can't pick up anything lower than 20 hertz. So in my illustration of a 1 hertz vibration, you actually wouldn't even hear that. It still makes sound waves, but when they reach your ear, they wouldn't cause your eardrum to vibrate back and forth. Your eardrum will only start vibrating back and forth a minimum of 20 times per second, which means a 20 hertz sound wave will cause your eardrum to vibrate, and you'll hear it, very low pitch. And your eardrum can, of course, vibrate back and forth 50 times per second and 100 times per second, and any numbers all the way up to 20,000 hertz, which is an extremely ear-piercing, high-pitched sound. 20,000 hertz means your eardrum is vibrating back and forth 20,000 times per second. But any sound wave that is approaching your ears that is a wave that's less than 20 hertz, again, it hits your ear, but it doesn't cause any vibration, so your brain doesn't interpret it as a sound. So you have, a limit, and all things do have limits. But we can talk about that more and specific detail. I want to show you some videos, but do realize that that all waves break into two categories. A traveling wave, moves. It could move rightward, it could move leftward, it could move upward, it could move downward. Like waves on the ocean, right? Those move sideways. How about a light wave? When you point your flashlight straight up in the air and turn on your flashlight, that light wave travels upward, right?
Yeah.
So any traveling wave is just moving through space. Could be horizontally, could be on a diagonal, it could be in any direction, but it moves through space. A standing wave is a little different, and it doesn't actually, once the standing waves are set up, the standing waves aren't really traveling left or right anymore. They're vibrating up and down. And so I think the best illustrated, because I don't know if you've even seen a video of this yet, I'm going to show you a video, because it's better to talk details after you've seen it for yourself. So give me a second here. So where is, just taking a second. You can see my screen, right? So you see that right there?
Yeah.
So you have a string that goes from one end to the other end, right? And then these things on the side, I can tell that this particular mechanical piece is actually one end of the string. Oh, did I just lose you? No. It's weird where it sometimes says I'm the last one left in the conference. So this particular thing on the left has an end of that string inserted into it, and then it swings it in a circle. So imagine you were playing jump rope, as a kid, and you weren't the jumper. Let's say you were somebody holding the rope. When you do that, you swing it, your arm goes in a circle, right?
Yeah.
And it causes the whole rope to go around and around. That's what this is doing on a small scale. It's actually whipping it around in a circle, but it still causes these wave patterns to be set up. And the wave patterns you get depend on how rapidly that circle is rotating. If it were to rotate really slowly, you might only get one loop. Well, actually, when you do jump rope, people are going around and around with their arms so slowly that you only see one loop, like the loops we talked about before. Remember, you'd only see one loop, and the person has to jump over that one loop, right? Yet, if you guys are doing jump rope with holding the ropes, swing the rope around faster, you can actually create two loops, and you could technically have two people. And I've actually seen people do that. You have to have a longer rope and two people that are willing to rotate it faster, and you can create two loops, and now you have two people that get to jump. Does that make sense?
Yeah.
And then the faster and faster you rotate it, you keep creating more and more loops. Because the faster and faster you're rotating it, the frequency of that rotation is going up because you're able to complete more and more rotations per second, higher frequency. And so when you keep creating more and more frequencies, when you keep creating higher and higher frequencies, more and more rotations per second, you keep getting more and more loops. So like in this picture, we're getting, how many loops are you seeing?
Right.
6 loops. And so it turns out, and I can teach you a rule for figuring this out later, but it turns out that's the third harmonic. So it's always half of the total amount of loops. Actually, that's not true. I take that back. That's another rule that I'm thinking backwards. It's the amount of loops that you see that creates the harmonic. So when you see one loop, that's the first harmonic. Like the jump rope, like I said, the simplest case jump rope, one loop that goes round and round, that's the first harmonic. When there's 2 loops, it's the second harmonic. 3 loops, third harmonic. So if you're counting 6, which it looks like, this is actually the 6th harmonic. I originally misspoke. So that's the 6th harmonic. And so if you watch, let's see what happens here. There it is. Oops. What happened? Shoot. Give me 1 second. Sorry, I didn't mean to do that. So, see if I can pause it. So, can you see that picture right there?
Yeah.
Which harmonic do you think that is?
The 1.
I know it's... Oh, well, you know what? Let me show you a different video. I thought that was going to be a little better than it was. Let me show you this one here. Because this is the one I do in class, and it looks like 2 teachers.
Standing waves are result.
Oops, sorry.
Waves are result of reflection, and standing waves are result of reflection and interference. As I send a single pulse down to this fixed end, you can see that it reflects upside down on itself. If I send a rhythmic pulse, it reflects on itself. This is the fundamental mode. Sending the pulse at twice the frequency results in the second harmonic.
So that one right there is the second harmonic.
Mm-hmm.
Now, you don't necessarily, like when you're doing it slowly, you don't, when I pause it, you only see one sine wave, like one curve, right?
Yeah.
Yet when we were doing it on the last video, it was going so rapidly that when we paused it, you could actually see the complete loop, right? And it's because it's moving so fast that it seems that the rope is up and down at the same time, but that's just an illusion, right?
Yeah.
So at any point, the rope can only be up or down. And so, like in this case, this is the second harmonic. If I go back a little bit, right here, they were doing the very first one. The first harmonic is like a jump rope.
Fundamental
Right there. See that?
Yeah.
You see that? That's called the first harmonic. And let's just continue seeing what they do here. So that's the second harmonic. And now, the things that you were referring to as nodes and antinodes, can you see my mouse that moves around on the screen?
Yeah, I know.
So this, do you remember what node means versus antinode?
No, this is when it's the point that like doesn't move.
Exactly.
It doesn't oscillate.
Exactly. So how many nodes would you see in the picture I'm showing you here?
3.
3, exactly. Where would the first one be if you're looking from left to right?
Where the first teacher is holding.
Yep.
In between the 2 antennas.
Yep, which would be right here, right?
Right there.
Yep.
And the other last teacher is holding.
Exactly. Yep. And so also, what harmonic is this?
The second harmonic.
So a second harmonic, and it has 3 nodes, right?
3 nodes, yeah.
So I'll come back to this video in just a second. I just want to jot that down because that's an important idea that you should ultimately learn. Let me see, where do I go back here? So traveling waves, and when he plucked it, that was the traveling wave. It was moving sideways, right? But after a little while, the first pluck that he makes, it reflects off of the back end where the other guy was holding it. And then when it comes back, it interferes with itself. And so I haven't taught you about constructive and destructive interference yet. But after those reflected waves interact with the upcoming waves that are still heading away, they end up creating this pattern called a standing wave. And the point is that once that standing wave is made, you don't really see leftward or rightward motion anymore. You kind of just see upward and downward motion. And all waves pretty much get broken into those 2 categories. So let me just erase. And so we're doing standing waves now. It's pretty poorly written. Sorry, give me a second. Okay, and so the first one looks like this, right?
Yeah.
And how many, and this is called the first harmonic, and it's also referred to as the fundamental harmonic, or sometimes just referred to as the fundamental. It means it's the base, lowest possible frequency that you can create on a string. And so I'm going to put harmonic. So this is 1. And then how many nodes does this have? Let's do nodes.
2.
Right, exactly 2. And then how many antinodes does it have?
1.
Yep, exactly. 1. Here's a node, right?
Yeah.
And then here's the other node. And then where would the antinode be? In the middle. Yep. The antinode is the part that is displaced the most. And displacement, like this part right here, is also displaced from here to here. And this part of the rope is also displaced from here to here. So which part of the rope has the greatest displacement? Right here, right?
Yeah.
And that's by definition what the antinode is. And so antinode was 1. Okay, so now let's look at the second harmonic. That would go like this. Here. This would vibrate. This part again would go up and down. And then again, this part over here, you know, would also go up and down, right? And so how many nodes does this one have?
This one has 3.
3, yep. I'm just going to put N for node right here in the middle, right? So node would be 3. And then if I go back to this picture, I just wanted to point out to you that in the, I didn't mean the picture, but in the video, you can see how nicely this looking at the center node, you'll see that it really doesn't move. It really does stay put. Where's my... So watch that middle piece.
Second harmonic.
Well, let's go back a little bit. Wait, look back a little bit more. See the middle part right here?
Second harmonic.
They didn't keep it going very long, but the middle part, that middle part doesn't really vibrate very much. Look at that one. See these nodes right here?
Yeah.
They don't really move very much at all. If they were doing it perfectly, they wouldn't move at all.
Mm-hmm. Yeah.
Okay, so my point that I want to make is there's a rule for, well, first, antinodes. How many antinodes are on the second harmonic?
So what we have here is the
Oops, sorry. This video is still going. Give me a second.
Wave driver, it's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy...
Sorry about that. So the second harmonic, how many antinodes are there?
2.
2, yep. So this one right here would be an antinode, and then this one right here would be another antinode, right? And so this is 2. And so based just on this, you can already actually discover the pattern. And actually the harmonic, what's called the harmonic number is referred to as n. So this is n equals 1, and this is n equals 2. And I could draw some pictures for you in a minute when we're done with this page of what n equals 3, n equals 4 look like. But just based on this, for the first harmonic, which is n equals 1, how many antinodes do you have? For the very first, so for the very first harmonic, which is called n equals 1, how many antinodes do you have? 1. For the second harmonic, which is called n equals 2, how many antinodes do you have? 2. So even though I haven't drawn it yet, for the third harmonic called n equals 3, guess how many antinodes you'd have? 3. Yep. So antinode here is always equal to n. Antinode number is always equal to whatever. So, and again, n is just a number that is an integer. So it's either an n equals 1, which is like the picture shown for n equals 1. If n equals 2, that's called the second harmonic. If n equals 3, it looks more like 1 loop, 2 loop, 3 loop, and then of course it would go like this. So this would be considered n equals 3, and that means this is called the third harmonic. Shoot. So for the third harmonic, n equals 3. And so this, if you want to think of it as an equation, you could, I suppose, but the number of antinode numbers, this box on the top right that I've drawn, is always equal to whatever n is. Right? Because how many antinodes do we have in this new picture down here that I've drawn?
3.
3, yep. Antinode here. Another antinode right here. And then lastly, another antinode there, right? So however many, whatever n is, if it was 10, you know, n equals 10, and there was 10 different loops, you'd have 10 antinodes. Does that make sense?
Yeah.
And then on the other hand, let me erase this for a minute. Well, I guess I can keep it here. What will be the equation for how many what will be the equation for how many nodes you have? Well, let's take a look. For the first harmonic called n equals 1, how many nodes were there? Now we're looking at nodes, not antinodes anymore.
There were 2 nodes.
There were 2. So it was harmonic n equals 1, harmonic 1, first harmonic.
Yeah.
Nodes number 2. For n equals 2, what was the node number?
There's 3.
3. So for n equals 3, how many nodes will there be?
4.
4. So you can think of this equation for how many nodes, this is the node number, is always n plus 1. I'm sorry that my writing is horrible. Let me try to be
Sorry.
equals n plus 1. So in the case that it was, you know, if someone said, how many nodes will there be in the 10th harmonic?
In the 10th harmonic?
Yeah, in the 10th harmonic, well, how many loops would there be in the 10th harmonic?
It would be 11.
So let's look back at the first harmonic. How many loops?
There were 2.
Look back at the picture.
In the first harmonic, there were 2.
No, loops. How many loops?
Oh, loops. I think you're talking about nodes, not 4.
Oh, it's okay. First harmonic, how many loops?
1 loop.
Second harmonic, 2
loops.
loops. So for the 10th harmonic,
There'd be 10 loops.
there'll be 10 loops. So how many nodes would you have?
11 nodes.
Yep, because this would be called the n equals 10 for the 10th harmonic, right?
Yeah.
10th harmonic would be called n equals 10, and so you would just say 10 plus 1 is 11 nodes, right?
Yeah.
Does that make sense?
Yeah.
Okay. Any questions so far in that? No? Okay, so I'm going to erase this. So let me give you a little quiz real fast here. So let's take a specific length, call it L, and now you've got two strings that are the same length. One is going to go like this, and then the other one is going to go okay. So question is, which string has the greatest frequency? This is string A, and this is string B.
String B.
B, exactly. String B is vibrating more times per second. And I know that's hard to see with the picture, but just think of it as like as the jump rope example I gave you that we do when we're kids.
Yeah.
When you typically go just at a normal human pace with your arms, you make one loop. To create two loops, what do you have to do with your arms? Make them move more frequency, higher frequency, make them move more times around per second, or less times around per second to try to make two loops with that string, with that rope.
More times.
More times, right? The thing that's causing the vibration has to take their arm up and down much more times per second, and the string itself will be vibrating around many more times per second. So this is the higher frequency. Higher frequency right here. And therefore this string produces more sound waves per second. And it would therefore be a higher pitched. Does that make sense?
Yeah.
And then another question would be, which string has the longest wavelength? So I haven't shown you this yet, so that was just me asking to see if it's something you read about or saw in the pictures. But I haven't mentioned wavelength yet. And so remember that one wave goes like, I'm going to draw something in the top right of the screen. One wave goes like this from here to here. That's considered one full wave from there to there. But whenever you see standing wave pictures in the textbooks, you see them the way I've drawn them in A and B. They show them as loops. It's only because they're vibrating up and down again so quickly that it seems like they're in both spots at the same time. But are they really? No. In reality, if you had a quick enough camera that was taking enough samples per second, high enough frame rate, you would notice that, yeah, they're only in one spot or the other. And so, for example, this wouldn't really be there, this piece right here.
Yeah.
It would just be like this, right?
Yeah.
And so, for example, the wavelength of this one right here is equal to L. Because it's one full wave fitting into a distance of L. So you notice how that one full wave is equal to the length of L that goes from here to here?
Yes.
So that wavelength is the length of the wave is L. Wavelength is equal to L. But when you go back down to this picture, if I erase this other piece to make it easier to see,
Print.
the one full wave for this one, if I start here, then I go up, I curl down through the middle part, I come around, and then I stop right there, right? Is that one full wave? From here to here, is that one full wave? Yes. So this is considered the wavelength of this particular vibrating pattern here. The wavelength now goes from here all the way to here. So now that you see that, we think about question 2. Which string has the longest wavelength? A, exactly. And remember another idea that we can pull from the last lesson. Give me a second. I'm going to ask another question, and we're going to see how that would have. The answer to this question would help you out. Would help you understand question 2 even more. So question 3 is, how are frequency and wavelength related to each other? Are they directly proportional or inversely proportional?
Directly proportional.
Which one?
Directly proportional.
So let's look at our picture again. Which one was the higher frequency? A or B? B. Which one was the smallest wavelength? B. So which one? Exactly. You see that idea? When you have a higher frequency wave, that it'll always be more scrunched inwards. It'll be like more like an accordion, like really crunched in, and you'll have many, many more waves jammed in there, and that makes each individual wavelength smaller. So that's a big idea with waves, and it's not true just for standing waves. This thing we're talking about right now is true for all waves in the universe. Any wave that you can think of that has a higher frequency will always have a much shorter wavelength. Let's take the opposite. Let's look at the picture A. Does picture A, again, have, comparatively, does picture A have a high frequency or a low frequency? Compared to, it's which one? Lower frequency. And then, so frequency is low, but how about the wavelength? Small or big?
The wavelength is longer.
Exactly, yep. So it's a lower frequency. Picture A is a low frequency, but the physical distance from one end to another end for one complete wave is much, much longer. Be true again for the guitars. This is the idea for like one of the strings that are lower on the neck.
Yeah.
Like the thicker strings. And then this one right here would be like one of the, I didn't mean to say that, sorry. What I meant to say is this top picture is like the ones that are higher on the neck of your guitar, the thicker strings.
Yeah.
Because when you pluck those, do those make a high pitch or a low pitch?
Low pitch.
Low pitch, which is a match with which pitcher, choice A or choice B?
Choice A.
Exactly, because pitch and frequency mean the same thing. When we think of high pitch, it's because there's a high frequency oscillation occurring that's causing many, many sound waves per second to be created. So choice A would be a low pitch, low frequency, because those mean the same, right?
Yeah.
But a long wavelength. And that's still in support of this bottom the answer to question 3, which is that they're inversely related, right? When the frequency is low, the wavelength is long. And let me also just say one more thing, or let me write one more thing here. The words that, the vocabulary that they use, I've been using it all along, but I haven't really told you. So vocab, actually, let me just erase. Okay, that's going to go away, it's fine. So let me tell you that the vocab for frequency is high and low. So people either say high frequency or low frequency, while the vocab for wavelength, the two words they use are long and short. Does that make sense?
Yeah.
So they use high and low as words to describe frequencies, and then they use words like long and short to describe how long the wavelengths are, long or short. And remember that when the wavelength's long, the frequency is going to be which one?
Low.
Low, exactly. So it goes across this way, right?
Yeah.
And then when the wavelength is a very short one, that will be
Frequency.
a high frequency. I was trying to draw arrows to show that those are opposites of each other because they're inversely related.
Yeah.
Okay. And now, all right, let's keep going. Any questions about what's on this so far on the board?
No.
Okay, let's keep going. Now, it also turns out well, before we keep going, I'm going to give you one more quiz here.
Mm-hmm.
1, 2, 3, 4, 5. I'm going to do the best I can to draw this because this is relatively difficult here. And it was just a couple years ago that they gave a question like this on a free response on the AP exam. They showed, in fact, what they do. Let me show you what they do. I actually do this experiment for my students in the class. Here's this guy right here. And let me see if he shows the whole picture of the whole system. Well, he's got one that's a little different. So actually, let me see if there's another one back here.
Standing wave can result of...
Sorry, one second. It's got to be one that I can see. So let me just type in standing wave demo hanging mass. I'm trying to show you the one that they actually used on the AP exam. And when my students saw this on the AP exam, they were thrilled because I did the exact same experiment with them and they could relate to it very easily. What's that? I'm sorry, I still couldn't make out what you said.
Oh, I understand what you mean.
Oh, right, yeah. So let me see. There's got to be. Did not think this would be hard to find. I guess this looks like it.
Of assessment data pairs.
Okay. Let's just see it in action. There we go. Perfect. This is exactly the way you. So take a look at what you're seeing there. You have two bars that are support stands, and then all they did was take a regular piece of string. You can do this any string you want. You can even do it with shoelaces, and you tie one over. They tied it on the right side. You see that here? Sure. So they tie the string there, and then this thing over here that you're seeing attached to this stand is just a vise, a little vise that clamps on here, and it's only support. It's able to support this pulley. See this little pulley here? Jeremiah, do you see the pulley there?
Yeah, I see. Yeah.
So this whole clamp that's attached to this metal bar is just there to support the pulley. So it keeps that pulley in that spot. And then you just, again, tie the string over here, you bring it over here, you let the string go around the pulley and down, and then you see there's a hanging mast there?
Yeah.
So that's exactly how the AP exam had presented this problem, showing the same setup. And then let's actually watch to see.
Wait, in the wrong position.
Now, it's too bad that he doesn't show it, but I can show you the idea on the picture. I'm just trying to pause this. So, because we haven't talked about this yet, but it's going to come in soon, is that when the string is under higher tension, think about your guitar, higher tension, does that cause higher frequency or lower frequency when you pluck the string? Exactly, because when you turn those knobs and you're tightening the string up, you produce higher pitches, higher frequency, right? So more loops are produced when the string is under higher tension. And so the purpose of that hanging mast that you saw there was to provide tension to the string. The string goes like this, and then there's a rod over here like this, and they just tie it on. There's little other things to hold it in place. But the point is, why is there tension in this string? Well, who's pulling down over here? Does this thing have weight? Yeah, and how do we calculate weight? Do you remember? What times what?
Mass times gravity.
Yep, mg. So depending on how much weight you hang there, more mass, more weight would produce more tension?
Yeah.
Yeah, exactly. If this was an extremely heavy object hanging there, this thing would be under very high tension, this rope here. And so when it's under higher tension, and we're going to come back to this in a minute, but I'm just pointing this out, that when it's under higher and higher tension and you allow it to vibrate, it produces higher frequency, higher pitch sounds. So I'm trying to just let you see the physical setup because it came up on the AP exam in the picture below. But back to the more abstract picture that they show in textbooks, like the one above. And so, in fact, actually, I think on the AP exam they showed both. They showed both these pictures. And so the questions for you again would be, what harmonic is this?
That would be harmonic.
Which one? Yep, good. How many nodes? How many nodes?
5.
5, yep. And then how many antinodes?
4.
Yep, good job. And how many antinodes is 4? Good. And then now I'm going to erase and have you compare these two pictures, this one and this one. This one's going to go this. And so this distance is, let's say, 5 centimeters. And this distance is 2.5 centimeters. And now the question is, which string, I really shouldn't say string, which vibration, I guess. Which has the has the greatest amplitude?
I would say maybe the first one. The first one.
Oh yeah, I forgot to label these. So this would be A, and this would be B.
It would be A.
Yep, exactly. So do you remember what amplitude? Before I even ask you, let's just see if you can figure this one out. Your first choice was correct. You said that the vibration has the greatest amplitude is A, right?
Yes.
Yep, and that's correct. Second question, what is the amplitude of vibration A and what is the amplitude of vibration B?
It's 5 centimeters for A and 2.5 centimeters for B.
That's a good guess. But remember that the definition of amplitude is not what you'd think. What most people would think is that the definition for amplitude is the distance from the top all the way to the bottom.
Oh, so they came from half the distance.
Yeah, do you remember?
For A, it's 2.5.
Yeah, so do you remember that amplitude? Yeah.
1.5.
Yep, exactly. And if you got that on the AP exam, are some of the, for a multiple choice question, are some of the choices going to be choice A? Let's say choice A would say vibration A has an amplitude of 5 centimeters. Will they have that on there?
Yeah, probably.
Yeah, 100%, because they're trying to see whether the kid or student has identified that amplitude is what you would naturally think, which is full distance from top to bottom. So they'll put that full distance on as one of the choices, or have they recognized it's actually only half? So A would only be, like you said, 2.5, and then for vibration B, it would be good. So far, so good, because we're just trying to tie back things from before.
Yeah.
Is that good so far?
Yeah.
Okay. So let's keep on going. I'm going to erase this now. So I am going to show you one more thing here. That the wavelength, this is again the symbol for wavelength.
Yeah.
You knew that already, so I don't have to write that in?
Yeah, I know that one.
Okay, so I'll erase that. So the wavelength of the nth harmonic, I will write it in. Wavelength where n can be any integer number, 2, 3, up to n, or up to capital N. But note that n cannot be equal to 1.2 or 3.67. They have to be integers.
Okay.
So that's an important idea, because if you looked at the first harmonic, how many loops were there? 1.2?
No.
No. How many loops?
1.
1. For the second harmonic, how many loops were there? 2.67?
No. 2.
2. For the next possible wavelength, what is the next possible wavelength? This one. How many loops? 3. Can you make any waves on the string that are in between those? The answer is no. No matter how hard you try, you cannot make another pattern that's considered a harmonic pattern that stands beautifully like a standing pattern, standing wave pattern that you saw in the videos. You can't make them with 1.67 loops. And the reason being is if you have 2 fixed ends that the string has to reattach to, right? It has to attach here and it has to attach here. So you can either make one, because that string has to come back and loop back down to tie in right here, right? And so this is the first possible one that you can make. When you have the same distance like this, well, we can have the string come up, the string can come down, and then someone might say, well, let's say it attaches down here. Will that make a beautiful standing wave? Turns out no. It'll be a jumbled mess, and it will. You might have seen that in the video. Sometimes it was just bobbling around. It wasn't making a beautiful pattern. And so it's because that string right here, and when you do that to make that beautiful pattern, you automatically fit exactly 2 loops. When you try to make something in between 1 and 2 loops, like 1.6 or 1.7, it doesn't produce a standing wave. It's just not possible. So it's important to note that when they say n is 1, 2, 3, 4, those are integers. That's the laws of the universe, that you can only make standing waves with those particular amount of loops. 1, 2, 3, 4, 5, 6, or 7, up to however many you want, but not 1.6, not 2.4. And that means they're quantized. The word, like you've heard of quantum mechanics before, I bet. Jeremiah?
Yeah.
Have you heard of quantum mechanics? So the word quantized, when it means quantized, just means that things come in specific units. Like eggs are quantized. You can get 1 egg, 2 egg, 3 eggs. You can't go to the store and buy 1.2 eggs. It just means that eggs are quantized. Turns out that standing waves are also quantized. They only come in 1 loop, 2 loops, 3 loops. But no matter how hard you try, you can't make any decimal 1.2 or 1.6 loops. Okay, so with that being said, and that's actually known as the boundary condition, which I don't know if that'll turn up. I don't think it would on your AP exam. But if you're going to be taking this stuff in college, which I think you are, these are called the boundaries, right? This is considered a boundary, and this is considered a boundary.
Okay.
And what's known as the boundary condition, in quotes, it's what you'd learn about in college, is what produces this law that you can only have 1 loop, 2 loops, 3 loops, or 4 loops, not a decimal. But I don't think that would turn up on AP exam. All right, so let me come back to where I was. The wavelength of any, back over here where we started, the wavelength of any harmonic, 10th harmonic, 20th harmonic, 3000th harmonic, there's an equation for it. I'm going to write it here and then show you why it is that way. It's 2L over N. Big box. You can solve lots of physics problems on the AP exam and from your homework using that equation. So let me show you why it is that way. It works. Let's go back to N equals 1. Oops, that's terrible. Okay. This distance is L. So what is the wavelength? Even without the equation, just what is the wavelength of that in terms of L? This is tricky, so take your time on this one. What is the wavelength of that loop in terms of L? Good job. Boy, that's great. Most students don't get that. So the wavelength of this is 1/2 L, right? Because oh, I'm sorry. I wish, because I said good job to you and made you feel great about it. It's actually the opposite. I didn't pick up on that. But that was a great guess, because most students would just say L. They look at that wave and say, that isn't that one wave? Because notice, to make one full wave, that would have to carry, this picture would have to carry all the way from here, all the way out to here. And that would be one full wave, right? So let me erase this bottom piece to avoid any confusion. Isn't that one full wave now?
Yes.
Yes. So in the very first, so in the very first harmonic, when you've got just one loop going up and down like this, how much of a wave is one loop? Is one loop a full wave or some other? It's half a loop, exactly. I'm sorry, not one loop is half of a wave, right? So the wavelength is actually 2 times L. Because remember, how long is L? L goes from here to here, and then another L goes from here to here, right? So that, what's the total distance? 2L. You see that?
Yeah.
So to go make one full wave, if I color it in, this is one full wave here. How long is that? 2L.
Yeah.
Does that make sense?
It does.
Okay, so my point is if you use our equation, we would say lambda 2, this means second harmonic. I didn't mean that. Sorry. I meant to say 1. Lambda 1, which means the first harmonic, you'd put in 2L, if I'm just following along with this equation right up here, right? And what number would I put in for n now for the first harmonic?
1.
1, yep, because the first harmonic is n equals 1. So in the denominator, notice the equation that I have in the box on the top right, n is in the denominator, so I would just put the number 1 here, right?
Yeah.
And that just tells me that the wavelength should be 2L. It's what we already had, right?
Yeah.
So let's see what happens when we apply it to the second harmonic. If we do the second harmonic, the picture would go like that,
Yeah.
and you get this loop vibrating up and down and that loop vibrating up and down. They'll tell you that the length of the vibrating string is L. And so what is the wavelength of this particular vibration in terms of L?
Wavelength equals L.
Exactly, wavelength equals L. Well, let's see what our handy equation up here would give us. You'd say lambda 2 is 2L over what n number is this? What harmonic number? Which n number? Remember, n. This one was n equals 1 when we had one loop. Now we've got 2 loops.
Yeah, I said 2.
Yep, 2, exactly. In fact, let me erase that. So this is now n equals 2, and so you'd put the number 2 in the denominator. 2 over 2 cancels, which this equation tells us that the wavelength of the second harmonic should just be L. Is that what we had?
Mm-hmm.
Yeah. I'm going to do it one more time, and then I won't go any further, but I want you to see how well it works even for the third one. So if you go back here, and now if I draw the third harmonic, how many nodes should I have?
3. 3.
So how many nodes do I have for the first harmonic?
You said no. I'm sorry.
It's okay.
You'll have 4 nodes.
You'll have 4, exactly. So this is what I think through. That's why I'm asking, just to help you see how I think. If I'm asking myself, okay, I've got to draw the third harmonic, I think, okay, how many nodes am I going to have? It's actually 4 nodes. So I make 4 dots equally spaced, 1, 2, 3, 4, and then I just draw a loop in between each of them, right?
Yeah.
The same thing. This is a length of L. What is the wavelength of this vibration? Let's think of this as 1/3 L. Let's think of this as 1/3 L. And let's think of this as 1/3 L, right? Because you can break it up into thirds, right?
Yeah.
So how long is the wavelength of that one?
3.
This is tricky. Think about it again. This is a challenging question. Very few students would get this first round. Try to identify where that one full wave is on that picture.
So would it be 1.5 L?
That's good. Yes, 1.5. Good. You have it. Yep. Exactly. 1.5 L. No, wait a second. Wait, 1.5. Oh, again, I jump at it because it's so close, but it's actually the opposite. Okay, so let's look at why. 1.5 L is actually 3/2 L, right?
Yeah.
1.5 is 3/2. So it's actually the flip of that. It's 2/3 L. The reason it's 2/3 is because I'm going to color it in. Where does one full wave go? I'm starting here. I color, color, color. I keep coloring. I keep coloring. And then where do I stop? Stop right there, right? So how many thirds is that? It's 2/3. You see that idea?
Yeah.
That's why this one will be correct. And so again, let's look at the point is when you have the equation, you could quickly just plug it in. So this says that the third harmonic should be 2L over what harmonic number is this picture? For this picture that we're working on. Yep, it's like the first third harmonic, so that would be called n equals 3. Yeah, they call that the harmonic number. And so what number would we put in the denominator?
3.
3. Is this equal to the same thing as just 2/3 L? 2L over 3, is that the same thing as 2/3 L?
Yeah.
Yeah. Is that what we had in our picture?
Yes.
Yes. You see how nice that works? So big box on that top right equation. It's certainly in your textbook, and it probably has a box around it too. I will tell you that it's not on the AP exam. What I meant to say is it's not on the equation sheet for your AP exam. There's a handful of equations specifically in this unit, waves, that are not put on the equation sheet. They expect you to memorize them for whatever reason. There's actually only one equation that they provide on the equation sheet for waves. And I'll show you what it is right here. It's the equation I gave you in the last lesson, which is that the speed of a wave is equal to the wavelength times the frequency. Remember this one?
Yeah.
That's
I wrote that down.
That's the only equation they put on the AP exam equation sheet for waves.
That is true. Okay, I don't remember.
So note to yourself that when you're getting ready to study for your AP exam, the one I just underlined is on the equation sheet. And all other equations that I'm giving you for this unit are not on the equation sheet. And you would have to memorize it.
Oh.
Okay? It doesn't mean because they're not on the equation sheet, you don't need them. You do need them. There's a whole bunch of problems that are multiple choice questions that you need this equation. For what reason, I have no idea. They don't put it on the equation sheet.
Probably to see if you really learn.
I guess. I mean, when you look at the equation sheet, have you ever seen it before?
Yeah, I printed one up.
Yeah, so if you've seen it, it's yeah, it's pretty in-depth. So I don't know. It's weird. In all of the other units, they pretty much give you all the equations on the equation sheet. They say we're only going to give them one. I have no idea why they made that choice for this one unit, but be aware of that. All right, so the very last thing is to, and then we can try some of your problems, is to recall that the speed of a wave on string, this can be for standing or traveling, because you can have a standing wave or a traveling wave, that the speed of the wave on the string is the square root. Do you remember what it is from the last lesson? And it's a ratio underneath
T divided by n.
Yep, the square root of the tension in the string.
Divided by the mass.
Close. The top part's right. Tension in string. The bottom part, the denominator, does involve mass, but it's not m that you put there, but it involves m. It was a new quantity that I don't think you had known about before that lesson.
Yeah, it was kilograms divided by meters.
You have it by meters. Good job. Yep. And the symbol is mu. It's the same symbol for like the coefficient of friction. It's the length of a string divided by the mass of the string. Oops, I'm sorry. I'm saying that backwards. It's the mass divided by the length. It's M over L. It's kilograms per meter. And that's referred to as the linear mass density. And that's the symbol, that's the quantity that goes in the denominator here.
All right.
So box around that one. Box around this one. And those are the only real three that you need. You can solve almost all problems with a combination of those three for this unit, more or less. All right.
Yeah.
And so remember the second equation. Let me actually show you this last thing. This last bit here. So, no, because I mean, it's one thing to have equations, and it's another to see how they come together. If I write this as the tension force divided by mu, and then notice in this equation over here we had V, right? V, right?
Yeah.
So can't we see from equation 1 that V is equivalent to the product of the wavelength times the frequency, right? Instead of V. You see that? And so now you can actually get a whole bunch of different results from that by making that substitution. You can get that the frequency, there's another very important thing that I haven't shown you yet. That the frequency is Ft over mu, and then 1 over lambda. That actually comes. See how you'd have to divide by lambda on the left side and divide by the other side by lambda?
Yeah.
So by multiplying this by 1 over lambda, so that's something you could jot down.
Jot down too.
Yeah, I would jot. I mean, just be familiar with. You don't have. So when I say to my students, at least, that these are the ones you have to remember. Oh, number 4 right here. Forgot about this one. The linear mass density one, 4.
Yeah. Yeah.
I tell the students, memorize 1, 2, 3, and 4. But then just be aware that you can make substitutions and relate, equation 2 to equation 4, or equation 1 to equation 3. And I'm trying to show you just one example of that. Because sometimes you have to manipulate different equations at the same time to produce something that they want for the exam. So like in this example, I'm showing you how we can relate equation 1 and equation 2. And instead of having V in equation 2, I rip away V and I stick lambda F there. And then, I can create this new equation for F that has the other variables in it. So it's like an equation generator, essentially. You just need equation 1, 2, 3, and 4 as your generator, and then you can mix and match them however you want to create other equations.
Gotcha.
And that would, let me just do one last thing. And I'm definitely, I'm just rewriting that one more time because that was kind of messy. Frequency is 1 over lambda. So I'm just giving you that as an example. And then one other thing that I definitely missed a huge part on, shame on me, so I'm glad I remembered, is this last bit. So can I erase this board at this point?
Not the last equation, not the last part yet.
Okay, I'll erase just the top part. So one last important part, and then we're going to just spend the remaining time letting you do your problems. And you only actually have 4 this week, so that's good.
Yeah. I'm done with the rest.
So the other really important equation is number 5, I suppose. So I apologize, I'm adding another one that you really should remember. But I'll put a star on it. Remember this one. Is that the frequency of the nth harmonic is some multiple of the frequency of the first harmonic. Lowest fundamental frequency.
Yeah, so I remember doing a practice problem on this type of question.
Yeah, because I can't believe I almost missed this. Because this is a really simple idea, and once you own this idea, this is one of the ones that stick for most students, and you can answer a bunch of questions with it. Just a picture, do you remember that the lowest fundamental frequency is just this one right here?
Yeah.
One loop, and it goes up and down. And so N goes here. I'll show you a quick example of that, and then we'll move on. Can I erase the bottom part now?
Yes, you can.
All right. So this is why this is so nice, because this is what I do in my room when I set that up with the hanging mass and the string, and I set it all up. The very first thing I do is figure out what the fundamental frequency is, and I literally have like a little box. And by the way, they could give this for your free response question. You get writing questions. I've said that to you, right? And they actually ask sometimes like you to describe an experiment, and you have to describe the materials and the equipment you need and how you would use it. So it's important, I guess, for me to even point out this based on that possibility, that this little device here has a cable, and then it goes over to this little, this is called an oscillator. And this is just a little piece of metal. It's just one piece of metal, and it vibrates back and forth. I know I'm drawing it like it's two pieces of metal, but it's just one piece, and it vibrates up and down. That's the part that oscillates. It's just a little strip of metal.
Okay, yeah.
And this is called the frequency controller. And it has a little LED display, which might say, 34 hertz on it. And it has some knobs on it. It has a frequency knob, and it has an amplitude knob. Okay? And so when you dial that knob into, let's say, 34 hertz, that little piece of metal will vibrate back and forth. Guess how many times per second?
30 times.
34 times. When you turn the frequency knob to 100 hertz, that little piece of metal, that metal strip, will vibrate back and forth 100 times per second. Well, guess where you connect your string to?
So a piece of metal.
To the piece of metal, right? And then you run your string over to a pole, and you just tie it. Does that make sense?
Gotcha.
And then you just need something to support this. That's called the ring stand that you saw in the picture. And so the first thing I do is, when I do this with my students, is I set up the fundamental frequency like this. The fundamental frequency is called the first harmonic, right? I never know what it's going to be. I just set it up, and I keep tweaking the frequency controller until I see that pattern, the one I just drawn. Let's make a simpler case and say that it wasn't a weird number like 34 hertz that I drew in here. Oops. Let's just say it turned out to be a nice number like the number 10. Of course, it could be any number. But let's say it was exactly 10 hertz. That when that thing was vibrating at 10 hertz, 10 times per second, we see that pattern. Then I tell my students, okay, how can we find the second harmonic? Because once that you have that knowledge is golden. The fact that the first harmonic is 10 hertz tells us that F1 is 10 hertz, right? That's what's in the equation. You see the box on the top, F1, right? So when N is 1, what is the frequency of the first harmonic? Well, let's see. Yeah, F1 will be 1 times 10 is 10 hertz, right?
10 hertz, okay, yeah.
Because the number 10 would therefore be F1. Then I say, okay, students, what will the what will the frequency of the second harmonic, F2, be?
2 times 10 would be 20 hertz.
Exactly. You see how nice and easy that is? What will the frequency of the third harmonic be?
30.
30 hertz. And what will the frequency of the 10th harmonic be?
Yeah, 100 hertz.
100 hertz. And so kids, are amazed by this. Heck, I'm amazed by it. It's amazing. So you do 10 hertz, like I described, and then we say, okay, well, if physics is correct, I should be able to take this little frequency controller, and it has a nice little LED display with digital digits on it. Kids always aren't sure if they believe me, so they come over and check, and I like that. And they see me dial it right into exactly 20 hertz. As soon as I dial it into 20 hertz, what picture do we see, or pattern do we automatically see get produced? Which harmonic will it be when we go to 20 hertz on the frequency controller?
The second harmonic.
The second harmonic. And as soon as you do that, just trying to finish erasing this.
You get the reading of one wavelength.
You get exactly one beautiful pattern like that, one wavelength. And the kids don't believe it, and they go, wow, it's exactly 20, if it was happened to be exactly 10 the first time. And then they're like, oh, that's just because it's the second harmonic. It won't work for the 10th harmonic. I say, yeah, let's try it. And then they say, well, what will the frequency of the 10th harmonic be for this? What would it be?
Yeah, 100 hertz.
100 hertz. I dial it exactly into 100 hertz, and guess how many loops they see?
You see 10 hertz.
They see 10. Notice that this picture that I currently have drawn for you is the second harmonic, right?
Yeah.
How many loops is there? How many loops?
10.
No. In the picture I'm showing you now, I'm sorry to jump around.
The picture you showed about the harmonics.
Yeah. So for the second harmonic, how many loops do you see?
You see 2.
2. So when I dial it into 100 hertz, in this whole example I'm doing on the board there, 100 hertz, oh, that's the 10th harmonic. Guess how many loops they see?
10.
They see 10 hertz, 10 loops, perfectly. So the point is that fundamental frequency is gold knowledge, because as soon as you know what that is, you can immediately figure out what any other harmonic is. All right?
Yeah, gotcha.
All right. And so I think there's one last one. I know I'm sorry, but keep adding to your list. There's really one last thing, because I had forgotten about number 5. You need to know this one. This one's really huge. This one's big.
Write it down. Yeah.
Yep. And then the very last one. Remember we wrote this one before? So the very last thing was to show you that the frequency of the nth harmonic is, because I know it's a little bit of a jumble, but remember that V is equal to lambda times F, right? So I'm trying to think of how do I jumble this around. 1 over V. Frequency and wavelength are inversely proportional. Give me 1 second to think about this. 1 over V. Oh, okay. That's what I'm trying to do. So if we take this one here and say, okay, frequency therefore must be V over lambda. You see what I did there, just to get this bit? If V is equal to lambda times F, then frequency must be V over lambda. And so this is the last one. I had it right there, but I want to show it like this. So now we're taking this and running with it and saying, okay, frequency is equal to V over our lambda. Is this the one I did for you? No, it's not. So notice I have an equation for lambda now.
Yeah.
So in for lambda, what we normally would put is lambda here in the denominator. I'm instead going to put in 2L over N. So can we simplify that? Yep, so that means we got a ratio already in the denominator, so can I reciprocate that up?
Yeah.
Yep, I end up with 2L over here like this. It turned out like this, with this times N. So this is an equation for the frequency of the nth harmonic. This is the last one I was trying to show you, and it's kind of a little messy, but let me erase this here. there it is, brush. Frequency of the nth harmonic, there we go. So that one actually is fairly important too. So know that one. I think that's number 6. I know, and there's a lot, right? And they only give you one, that one that's on the bottom left of the screen. All right. And notice that lastly that the frequency is proportional to n, right?
Yeah.
So as n goes up, what happens to the frequency?
Goes up.
How about me and you are holding on to a long, long string? Or no, let's say we're holding on to a relatively short string that's only 5 feet long or something. I'm holding on to one end, you're holding on the other end, like you saw the video. And I start vibrating. You know, my hand goes up and down at a certain rate. Let's say we see a certain pattern. Let's just say we see the second harmonic. We see 2 loops, and then we say, okay, let's take out a new rope. It's made of the same material, but it's going to be a lot longer this time. A lot longer. So L is greater. And we say, now I'd like to make the second harmonic. Yet again, we first made the second harmonic with a short piece of rope. Now we're taking a longer rope and again trying to make the second harmonic. Would we have to go up and down with our hand faster, or up and down with our hand with a less of a frequency to again make the second harmonic based on number 6 equation? If the length goes up, what would have to happen to how rapidly our hands go up and down to produce the second harmonic? How is F and L related in that equation?
F and L are inversely proportional in this equation.
Exactly. So if the L goes up because we take out a rope that's much longer, and we still have to produce N of 2, so N's fixed as the number 2. Longer rope what would we have to do with it? What would that do to F?
Make it short.
Yeah, a lower frequency. We could actually go up and down with our hands slower to produce the second harmonic. I mean, you're not going to memorize all those, obviously. I don't even memorize all of them. But the point is, once you have a handful of these and you can use inverse proportions or direct proportions, you can solve a lot of those concept questions like the one I just asked. And remember, they give a lot of those on the multiple choice. Okay, that I think finally concludes it. I know it was quite a bit, but let's take a peek now. Number 48.
42, I believe. No, 48. You're right.
So I hope you get 50. I was reading through these to be the way. 54. Or 48. This is another part that I haven't been able to get to. In fact, I think the guy showed it. Might still have him here. Yeah, right here. Notice what happens after it reflects.
It's a result of reflection and interference.
So he's going to move it. You're going to see the wave start traveling to the left. Notice what happens after it bounces off, or that's called reflecting, off of the left side. Watch what happens.
As I send a single pulse down to this fixed end.
Ooh, did you see it?
I think I missed it.
Watch closely. It's tough.
End. You can see that it reflects.
So notice that when he makes the wave, the guy on the right,
Yeah.
the wave is traveling on the top. You see that?
Yeah.
But what happens after it bounces off him? Watch. Where is it now?
It's at the bottom.
Yeah. You see that?
Yeah.
So going back to your problem, that's exactly what they're referring to there. Oh, I thought it was. I apologize. Oh, this is a different one. Boy, there's so much information in this. This is an interference. So he gave you one interference problem. All right, let me jump back. So there's waves can add or subtract from each other. Did you read about constructive and destructive interference?
Yeah.
Okay, so I'm not going to say all of it, but I'm going to just point out the main ideas. If you have a wave that's like this and another wave that's traveling like this, and they're traveling towards each other and they're going to collide. Here's V, V is this way. And let's say the amplitude of this one is 2 centimeters and the amplitude of this one is 2 centimeters. Then it turns out that when they actually collide right here in the middle, that's called, do you have a guess of whether they'll make constructive interference or destructive interference when they collide?
Destructive interference.
So it turns out that since this one is already upwards, the pulse is already on the top, and the other one has a pulse that's on the top, those add to each other. And when they add, they'll produce an amplitude that would be 4 centimeters. See, so because what was the amplitude of the first one? 2. And then what was the amplitude of the other one? 2. So when you get what's called constructive interference, the amplitudes add. Oops, sorry. So that means that whatever the wave is, it'll get more intense. If those were 2 sound waves, then in that center spot, all of a sudden those 2 sound waves, when they collide in the center, you'd hear a louder sound in the center. If it was 2 light waves traveling towards each other, the light would seem brighter where they meet at the center. If it was 2 ocean waves traveling towards each other, and you can see this just by watching 2 waves collide, the heights of the waves get added, like I've shown in the picture here. That's called constructive interference. On the other hand, can I erase this? What's called destructive interference is like a picture that you're showing, that they're showing you in your book. You can have one that has a pulse. This is referred to also as a wave pulse. Notice that the wave pulse doesn't have the very full picture we've been talking about. It's only half. You see that? It's only half of it.
Yeah.
And so you could have one wave and then another wave, again, traveling towards each other, and they're going to collide. And you could have the amplitude of this one be 2 centimeters, and you could have the amplitude of this one be. And notice that for wave pulses, the amplitude is not half of what I'm drawing. The amplitude is the full distance from the center of the rope to the top. You notice that?
Yeah.
But for the old waves we were talking about, if this full distance was 4 centimeters, then the amplitude would have been 2 centimeters, right?
Yeah.
So when you're looking at wave pulse pictures, the amplitude is just from the middle up to the top. You don't half it. And so the point is, when these 2 waves that I've drawn in this top picture here collide with each other, they actually destroy each other. That's called destructive interference. And so you can think of this height here, since it goes down, you can think of this as a negative 2 centimeters because it goes downwards. And you can think of this one as a positive 2 centimeters because it goes up. And there's another word here. It's called superposition. It is the idea that waves can add when in the same spot in space. So when 2 waves are traveling through space, they can be at the same point at the same time. And the idea of what's called superposition is that, but when they're in the picture, like the picture I've shown you, if one of the wave pulses is down and the other wave pulse is up, when you add up those, notice down has to be considered negative 2 centimeters, and the upward has to be considered positive 2 centimeters. What do you get when you add those amplitudes together now?
Would be destructive.
It'd be 0, exactly. And it's got to be a cool, I know Wiki has some pretty cool animations. Let me just see. Destructive. Yeah. That's not going to do it because they're not doing it quite right. So don't even look at that. Let's see. Well, I don't know that I'm going to be able to show it to you, but what you'd see, I guess I can try to draw it. The best I'll do, or the best I can do is try to draw it. So what you'd see is that the waves, like in the first case scenario, remember they were both heading towards each other, like one was up and the other was up. One is up, the other is up, and they're traveling towards each other. Well, right when they meet, they'll add up like this, right? But then a moment later, this one, if I call this wave A and this one wave B, a moment later, wave B will still be heading to the left like it originally was, and wave A will also still be heading to the right like it originally was, and they'll both be the exact same amplitudes, as if they never even touched each other. So that the point is that when they add up, it's only in that brief moment when they're occupying the same point in space that their amplitudes add, and then they just continue on like they never even met. Does that make sense?
Yeah, that's
A little bit?
yeah.
Like if it was water, the height of one of the water waves and the height of the other water wave add, so it produces one big water wave, taller water wave, but just for that moment. And then those individual waves pop out from each side and continue along in their same directions they were originally going. And that's the idea. When you're doing the problem like I'm showing you on the top of this page here, turns out that right when they meet, what will their amplitude be? So notice that one in this now that's left on the page, one of them is a pulse that's on the bottom of the string, the other is a pulse that's on the top of the string. Exactly. That doesn't mean that after they collide, no waves exist anymore. It just means just for that brief moment when they reach the same point in the rope, one would still be here, and then, when they get closer, they'll still be like this, right? And then there's just this, let's say at T1. Then at a time a little bit later, all of a sudden, when you look at the rope, what will you see? Nothing. It'll be flat. And then a little moment later, guess what you would see? Would there be just nothing again?
No, the waves would go back to the original amplitude.
Yep.
Up and down.
Yeah, this is another weird thing. So when they're opposite, they get flipped.
Yeah, that's what I meant.
Yeah, I know. So like, if this was wave A and this was wave B, this is A plus B. Yep.
Wave B would be on top.
When in same position. And then when they continue on in their merry way, a moment later, A will be on top. Is that what you were just saying?
B would be on the.
And B will be on the bottom. So remember, which way was B originally going? To the left. B will still be going to the left. It's just that he gets pulled to the bottom. And wave A, which is going to the right, will still be going to the right. But since he was originally on the bottom, when he interacts with that other wave, the other wave lifts him up. Wave B physically pulls upward on wave A and lifts him to the top. So when they finally pop out of each side, they're flipped. So does that make sense? I know that's a weird idea, but that ends up being what happens. But let's do another case. Let's say, like in the problem they're giving you, let's say they're not exactly the same amplitude, which it looks like they're not, right? If one of them, let me read it again. I'm moving forward to sketch the shape of the string. At the moment, they directly overlap. So let's say one of them goes down like this to, and this is 4 centimeters, and then this one is only 2 centimeters. What would the sum of those waves be when they meet? The amplitudes. Notice that in the first case, I showed you, that's still on the top of the page. They're opposite sides, one's on top, one's on the bottom, but they were equal amplitudes. One was 2 centimeters down, the other was 2 centimeters up. Now, the one that's down has a larger amplitude, 4 centimeters, and the one that's up is a little less amplitude of 2 centimeters. So what would the sum of their amplitudes be when they collide? Which way would it be would it be pointing up or down when they collide?
Down.
Yeah, but with what amplitude? 2, exactly. Yeah. Down, this would be 2. This would be the A. If this again was wave A, and this was wave B, this would be the wave A plus B, with an amplitude of you can think of it as -2, because this other 4 was really -4, right?
Yeah.
And this one was +2. Does that make sense? So when you add them, -4 plus 2, you get -2. So that's the idea of that. What would happen because we're running out of time, but how would you describe your answer to part B?
How would I describe?
Yeah, to sketch the shape of the string a few moments later. If the wave on the left is wave A and the wave on the right is wave B, where will wave A be? Still down or up? Up. And traveling which way?
So, right.
Yep. And will he have the same shape that he has now? Same general shape?
Yeah.
Yeah, same general shape. He'll just be facing up and still traveling to the right. And what will happen to wave B?
Down, going to the left.
And the same general shape as well.
Yeah.
Yep. And then I'm reading C. At the moment the pulses pass each other, the string is straight. What has happened to the energy at this moment? Oh, I can't believe they've asked that. I've had significantly long philosophical debates about the answer to this question. Yeah, because it's actually a deep question in physics. So all I'll tell you is I don't know the answer to this question. I think that they want you to say a certain answer, and I'll tell you what they want you to say, but I don't agree with it. But know that write this down in your notes, that the energy of a wave is proportional to its amplitude. That might have been in your notes from the last lesson. So taller waves inherently have more energy. The amplitude squared. That's another detail. But the point is, as they're saying in question C, At the moment those two pulses hit each other, they cancel each other. That's called destructive interference, and the string is perfectly flat. What would the energy be of a string that's perfectly flat?
0.
It would be, exactly. However, I believe that the string is being compressed. When those two waves actually hit each other, like anytime like two cars hit each other, they compress each other, right?
Yeah.
And so I feel that the energy so when it's flat, there's no energy due to the wave anymore. That energy has been turned into the compression potential energy. Yeah. Yep.
Turned to compression.
Exactly. And then it doesn't want to be compressed when it's flat like that. What does it do? Spring back out, and it recreates those waves.
I still see why you would. What brought you to that conclusion, honestly?
A little louder, I'm sorry.
I said I see why that's your personal
opinion. Yeah, that's my opinion. So I think they. Yeah, I think they wanted you to say that the energy is 0, and that would be a violation of the conservation law of energy, because you can't just get rid of energy. So it has to go somewhere, and it wouldn't be in this traveling wave anymore. It would be, because I've seen the similar question on AP exams, and when I looked at their scoring rubric, there was no real description of what I just told you. So I think my response is a little more thorough, that it would technically compress the rope a bit, and have to be, because the energy of that wave has to go into something, and then the rope would then spring outward to recreate those waves.
So what would be the number of that compressed energy? Like, it wouldn't be 0. You're saying, would it be like the additive?
So since everything, let me erase something over here. Since all things can technically be compressed, even though like in physics we talk about idealized objects like springs, you can compress anything. You can push on a piece of glass and technically make those glass molecules might move slightly closer to each other. I mean, you can warp it, right? You can push on a piece of glass hard enough where it starts to flex and bend. And then when you let go of it, it flips, back to its original shape. And that means there was some sort of compression occurring when you did that. And I'm sorry, let me erase this. So the point is that even though they talk about things like springs, everything can be compressed. And from a while back, the potential energy of anything that has spring-like properties, which means it has to have some elasticity, is 1/2 k delta x squared, or delta x is remember the elongation, or how much it's been compressed. So however much energy was in that wave, that amount of energy then gets immediately turned into spring elastic potential energy in that whatever the medium is. If it's a rope, in that amount, like if you knew that the total energy of the wave was 40,000 joules, maybe one wave was 40,000 joules, the other wave was 40,000 joules. Well, in this collision, there should be 40,000 plus 40,000 should be 80,000 joules, which means you should be able to put the number 80,000 joules in here. And if you knew the elasticity, that's called the spring constant. It's really referred to how elastic a certain material is. You could predict how much, this is the compression here, you should be able to predict how much compression there would be. And it would be like that just for a brief moment, just like a tennis ball. You can compress it, and then when you release it, it uncompresses and then turns that back into kinetic energy for you. And so in that brief moment when the rope is flat, there's no kinetic energy because it appears that it's just flat and not moving. But then when it unsprings itself, just like the tennis ball, it returns that energy as kinetic energy of the waves back.
Okay.
That's a very deeper level question. But that's that. And then I know we're almost at time, but I want to just point out just a couple things. 50, we're not going to obviously do them all, but I just want to give you some hints. I think, so I'm not going to give you too many hints. So, well, it depends. Do you want me to give you some hints or not? It's up to you. Okay, so they'll be relatively quick, but and I don't memorize everything. It might seem that way, but I actually figure a lot of stuff out as I'm talking because I can only memorize so many things. So like the ones I've told you to memorize, I memorize those, but all the possible combinations of equations, I can't memorize them. It's just too much for my brain. So for example, there was one that I told you that was Fn is, can you tell me what that was for, with L in it? It was proportional to N, and then
which one?
This was like 2L.
Times Fn equals N times V over L.
V over L. V over. So give me one more second. Oh, I take that back. Sorry. Look at number 50. So number 50 is saying you've got a string vibrates at 294 hertz. What frequency will it vibrate when it's only 1/3 of its length? Right? So the original length is L, and then it's saying once you're only at 1/3 of L, what will that new frequency be? So well, I suppose that means that how many loops are in here? There must be 3 in this one. In the original one, there must be 3 loops, which means if you pinch that string all the way down to 1/3, how many loops would there be? If the original L has 3 loops in it, and then it says
you. So 1/3, it only have 1 loop.
1 loop. So by what factor would the frequency decrease by?
By 2/3.
So if it's originally 3 loops and it goes only to 1 loop, frequency has gone down by a factor of what?
The frequency has gone down by a factor of 2/3. Yeah.
Down by a factor of 3.
It loses 2/3 of its length.
So it goes from this one to just 1 loop. So this frequency would be only 1/3 of the old frequency if this was F2 or F1, sorry, and this was F2. So what I'm pointing out is if you go from 3 loops to 1 loop, then the frequency drops by a factor of 3. Or if you go, let's go the opposite way. If you go from 1 loop to 3 loops, then your frequency would go up by a factor of 3.
Okay, yeah.
Does that make sense?
Yeah.
So if you're going, they're saying you're going from 3 loops down to 1 loop, frequency should go down by a factor of 3. So it means you would multiply by 3 or divide by 3.
Sorry, you would multiply by 3.
Now, so if this frequency up here was,
it should go down, right?
let's say this was 100 hertz.
It goes up, right?
Let's say this first one with 3 loops is 100 hertz. What frequency would this one be here? It'd be 100 divided by 3, right?
Yeah, 100 divided by 3.
33.3 hertz. So that's I actually did that one for you. I shouldn't have done that. But it should be 1/3 of whatever that old frequency was. It's saying you're taking the length of your string and shortening it down to only 1/3 of the original length. And so therefore the frequency would drop by a factor of 3. Does that make sense? So that means you just take whatever that original frequency was and divide it by 3. Because remember, the first harmonic has how many loops? 1 loop. The second harmonic has 2 loops. The third harmonic has 3 loops. And do you remember that the frequency of any harmonic is n times the fundamental, right? So that means that the third harmonic will have frequency.
Yeah.
And so that means the first harmonic would be 1/3 of the third. So I'm nearly certain that that's correct. I'm almost 100% sure that that's correct. But I'm actually not going to do the other ones. But I can maybe give a Yeah. I think you're better off. You only got 2. I was thinking you again that when I started saying that you had like 8 or 9, but I forgot. You only have 4.
Mm-hmm.
So I'd say try those other 2. That'll be good practice for you.
Okay.
Just remember there's a good amount, like 5 or 6 equations, and you'll be lucky if you could just grab one and be like, oh, I can solve it just with this one. Sometimes you can, but when questions get a little harder, you have to grab sometimes 2 equations and kind of manipulate them around to get the variables into one equation that addresses the things that question's talking about. If that you know what I'm saying?
Yeah.
And it takes a little bit of what I call algebraic manipulation. And in those cases, you have to start potentially with 2 equations. And so when you read the problem, identify which variables they're talking about. Let's say, for example, they mention velocity and they mention I don't know, velocity and length. If they mention those 2 variables, you might say, oh, okay, let's look at the equation that says v equals lambda f. Well, velocity is in it, great, but is length in that one? Not really, right? V equals lambda f might not have L in it, but you might have to work out, well, is it 2/3 L or is it 1/3 L, like we talked about earlier in the session. So you kind of have to be creative with some of these to
figure out the equation.
Yeah, exactly. So I think it's good practice for you. You only have 2 there, but I would give them your best shot. And actually, I'm just curious again because I didn't remember exactly where it was. So actually, I don't think 54 was. Where's 54? So I didn't get to see 54. So 54 was your last one, but it didn't. It got chopped off on this one. Yeah,
I'm sorry.
that's okay. So give it your best effort, though. And hope that was helpful for you. And I plan on seeing you next.
Thank you very much.
Oh, you're welcome, Jeremiah. And I'll plan on seeing you next week.
Yes.
All right. Have a good night.
You too.
All right. Bye-bye. That concludes today's lesson with Jeremiah, Boston Dream Academy, Jeremiah LaRoche. Starting time was 7:10 p.m. and it is now 9:10 p.m. So it was a 2-hour lesson. Today's date is February 26th, which is a Sunday, and lesson has completed.